Yeah. Okay, let's begin. Welcome to the second day of our math and machine learning closing workshop. So we're truly delighted to have Yang-Hui He direct from London. Yang was really very much a pioneer in this business of applying machine learning to mathematics, to finding patterns. He has a very long publication list and has discovered many remarkable patterns in mathematics. And so it's the perfect person to give us an overview of the field. Yang?
Okay. Thank you very much, Mike. Thank you for this kind invitation. It's a great honor to be speaking here. And I apologize I can't be there in person, especially since I have so many friends over there and probably in the audience right now. So I'm certainly there with you in spirit. Let me just begin a little bit to tell you where I'm actually calling from, mainly for two reasons. One is because well, actually, the first reason is that there's a typo in my. I just noticed this morning there's a typo in my affiliation. So I'm calling from the London Institute for Mathematical Sciences, here situated in the Royal Institution, which is Britain's well. It's UK's first independent research institute for mathematics, modeled after the IIS in Princeton, and it's founded about 12 years ago. And I joined about 3 years ago. We're housed in the very rooms that Faraday used to live. And one very important thing is that we announced 23 challenges, and one of our major, well, 23 for obvious reasons. And one of our major challenges is AI for mathematical discovery. So it's very beautiful, and I encourage all of you to please come please come and visit us in London. I think many of my friends have been in these rooms. So as Mike suggested, I'm supposed to give somewhat of an overview about AI-assisted mathematics in the last decade or so. And I highly encourage you guys to read some of these reviews. There's one that I wrote some in 21, and then in the past years there's a beautiful review by Mike about machine learning as a tool in theoretical science, and then in these two reviews which just came out in the last couple of months, one by myself and then one by my friends Sergey, Jim, and Fabi. So in this talk, I'll mainly give some thoughts on how how humans do mathematics in three ways, which I try to classify as sort of borrowing words from theoretical physics as bottom up, by which I mean mathematics as a formal logical system. And top down, which I try to argue is mathematics done as a creative or intuitive art, and meta mathematics. I'm borrowing this word from meta science, of mathematics done as from a point of view of language. And this is kind of interesting. The third direction is kind of interesting, is because one could even perhaps do a little bit of mathematics without any understanding of mathematics. I will mainly emphasize on this top-down approach, which is very much in the spirit of what I've been doing in the last 7 years or so, which is to just try to use machine learning and tools from AI to help us with this intuition of human intuition, for which I will mention later. There have been various progress, and of course there's this famous DeepMind paper of Jordi and Alex Davis. And then some of the work that I've been doing with Q Huan and Tom Oliver and Drew Sutherland and Alexei Pozdnyakov on murmuration conjectures. And I'm very happy that Q Huan is there to tell you more about the murmuration conjectures in detail. So I will give a little, so I won't go too much into detail and stick to sort of the overview. So I think I'm preaching to the choir in this audience that the 20th century has been very much an era of computers in mathematics, and hopefully by the end I will get to the point I will try to say that 21st century is very much a collaboration between humans and AI systems for mathematics. one thing I just like to emphasize is, there are major results in mathematics. We've certainly reached the point, even by the 20th century, there are major results in mathematics which could not have been proven without the help of computers, such as, the four-color theorems or the Kepler conjecture. And what's really interesting is a lot of this the classification of finite simple group problem is really I like to quote some experts in this field, people like Peter Cameron and friends, who very astutely point out that no human has actually read the entire proof of the classification theorem. And something that I suggested to Kevin Buzzard is to try to formalize this, and perhaps someday we'll get to the formalization of this problem. So let me begin. As I said, there are three directions. So let me begin with this bottom-up approach. And so, one could really think about bottom-up mathematics going back to the beginning of the 20th century, perhaps even to the end of the 19th, or even back to Leibniz, or maybe even back to Euclid. There's always this idea of axiomatizing mathematics. And I think the first really serious attempt is this program of Principia Mathematica. And of course, it's well known that this program was killed within 20 years, right, because of the incompleteness theorems and undecidability theorems. But nevertheless, I like to quote my very distinguished colleague, Professor Min-Young Kim. He says the practicing mathematician hardly ever worries about Gödel, in the sense that if you have to worry about whether your theorems are decidable or not on a day-to-day basis, you'll probably get very depressed very quickly trying to do research. So the point of this is that the two negatives cancel each other out. And despite all of this, there has been very much an active program in proof assistance. And this sort of goes under the name of the ATP tradition. So the automated theorem proving. And this is a very, very long tradition. For example, in 1956, Newell, Simon, and Shaw were able to actually devise a very, very primitive version of the computer to prove some of the statements in Principia Mathematica. And so that really kickstarted this idea of using computers to aid proof. What's really, really interesting, I would like to point out, is that 1956 was also the year of 56, 57, was also the first time that neural networks were devised. In the bottom, I think, in the basement in MIT and Penn, they were trying to literally use photoreceptors to devise the first neural network. So even in the mid-50s, people were thinking about this idea of having artificial intelligence, which has now come to be known, to try to help with problems in logic and in foundational issues in mathematics. So, of course, I'm certainly no expert in this ATP program, but I keep a keen eye on this, especially since the Coq and Lean systems have become very advanced now. And people like Davenport and Kevin Buzzard have been very much proponents for this proof assistance. And I think in the words of Terence Tao, I think he calls these systems proof co-pilots, which is, I think, a very astute way of describing what these things are. So I think one of the highlights of this is this 2023 paper of Gowers, Green, Manners, and Tao, where they actually used Lean to proof check their proof of the polynomial version of the Freeman-Rouget-Montan conjecture. So this is very nice. And Szegedy and DeepMind, extrapolating on two data points, I have no idea how they extrapolated this, but since computers beat humans in chess in the 90s, or in particular, DeepMind beat humans in chess in the 90s, and then Go in 2018, it might beat humans in proving theorems in 2030. I don't know where this number comes from. And talking to experts like Kevin Buzzard, he says, he goes up and down whether he wants to decide whether this is an underestimate or an overestimate. So that's all I'm going to say about this entire program about the proof copilot, which is very, very much an active research area for the last 70 years. And I refer you to these recent beautiful lectures by Terence Tao online about this idea of using formalization techniques to prove theorems. So let's move on to mathematics as a language. So bottom up is going up in actually line by line of constructing mathematics. And mathematics, which I also won't say very much, is sort of trying to extrapolate information about mathematics purely from a linguistic point of view. One of the earliest things that we tried was this paper that I did with Jajali and Nelson. I mean, this is obvious what one should do, which is just take archive and try to learn that linguistically. And what's interesting we learned from this was the following experiment, which I'm just going to say which is a lot of fun, which is if you take the archive and if you take Vixra, for those who might not know what Vixra is, it's archive spelled backwards, and it's essentially all of the rejected papers from the archive. And what is really interesting is that Vixra is an incredible repository of fake science, basically, of like crackpots and whatnot, who have, all the papers that are, clearly wrong, and, like one-page proofs of the Riemann hypothesis and whatnot. So we checked linguistically archive versus Vixra, and you find that even though Vixra has the right buzzwords as archive, which is real science, but different sections within Vixra, unlike archive, even on a level of titles, they're not the confusion matrix in classification of their linguistic structure. Just using Word2Vec it's not distinguishable. So, like in archive, a paper in pH, which is phenomenology in high energy physics, versus theory in high energy physics, fairly well, whereas in Vixra you don't. So it's kind of interesting that the language of science is distinct in its linguistic structure from language of pseudoscience. So this is kind of fun experiments that we were able to tell. Of course, this has gotten increasingly serious. In 2019, this paper of Chitoyan in Nature used Word2Vec, and they were actually able to discover new reactions for material science. And then there's these beautiful papers, which started in the 19 of Charton, I think, who was one of the organizers of this conference, which is just a deep learning for symbolic mathematics, where they use the sequence-to-sequence models to actually predict new integral identities. 2022, which is very interesting, it's a bit surprising that in 2022, one of the most remarkable things happened in human history, and yet it wasn't all over every single newspaper headline. ChatGPT has actually passed the Turing test in 2022. And it is what it is. We have, certainly in 2022, by today's standards, I think it's pretty much indistinguishable whether you're talking to, having a casual conversation, whether you're talking to a person or talking to a chatbot, which is quite impressive. And this is one of the reasons why ChatGPT can do, so many tasks so well. And of course, now in the last 2 years, this idea of the large language model for mathematics, notably DeepMind's FunSearch, OpenAI's QStar, Meta AI's Llama, DeepMind's AlphaGeo have done wonders to language models for mathematics. I think Llama actually has taken, to my knowledge, all of the archive and has learned that linguistically. So sort of ChatGPT for the archive. It's worth pointing out the DeepMind's AlphaGeo. So with this 53% is what in 2023 AlphaGeo was able to perform on the International Math Olympiad level in Euclidean geometry. And of course, this was famously improved just a few months ago by AlphaGeo 2, where they can perform to 84% accuracy, which is enough to win you a silver medal, right? So the point is, of course, for very specific problems. So they trained their network on their language model on solving Euclidean geometry problems in the International Math Olympiad. And this is towards answering the grand IMO challenge. And I believe that DeepMind is now working on alpha proof, which is some version of large language models plus lean. And that would, and hopefully in the foreseeable future, they will start generating new pathways to proofs, and instead of just using lean as a co-pilot in checking proofs. So this is very interesting. So basically, I think the punchline is, given this fact, the AlphaGeo2 has achieved 84% accuracy in IMO Euclidean geometry problems. I think there's been a meme going around that AI now is approximately equal to the 12-year-old Terence Tao. I think this is a very good comparison, because I think the mind of Terence Tao is a very good and gold standard for what human imagination is, and AlphaGeo2 can perform just like the 12-year-old in some vaguely defined sense. So I don't know. Basically, if you reach the 16-year-old Terry Tao, you're really deep into the land of creative and research level mathematics. So now let me focus on the main direction of which I think the last number of years has seen tremendous progress, which is top-down mathematics, which is this intuition, experience, and experimentation, and how AI can guide us in doing this. So needless to say that mathematics really is done top-down. Nobody does mathematics bottom up. We all write our papers backwards, right? We muck around with experimentation, and then we write our papers backwards with definitions, lemma, and proofs and whatnot. But what we actually do is to really gain a lot of intuition and experience, and then start to formulate it seriously. So I apologize to my friends who have seen this joke before. What is the best neural network of the 18th and 19th century? Well, it's clearly the mind of Gauss. And this is kind of experimentation that I want to emphasize, right? The history of experimental mathematics it goes back to the very beginning. So, but this is very much a beautiful example, that Gauss was able to plot the prime counting function pi of x, and just look at this and recognize that this is x over log x. It's important to point out that Gauss, once he had prime tables, but the tables only went up to hundreds of thousands, and he actually had to compute by hand some primes, very, very large primes, in the tens and hundreds of thousands. And he actually got some of them wrong, but nevertheless, it didn't affect the general structure of this. So this kind of conjecture formulation is in fact even tolerant to small errors, and also what's important is that this conjecture was made before Adamard and Delavalle-Poussin proof of this prime number theorem, because these gentlemen needed Cauchy and Riemann to formulate complex analysis to even prove this. So it's kind of, how did Gauss get to this? Of course, Gauss was inspired by the works of Legendre, who had some preliminary versions of this. But how did these people even come up with this? So that's very, very interesting to see what what was going on in terms of the experience and in terms of what they're going in their mind. So now fast forward to the 20th century. The BST conjecture, of course, is still an open problem. This conjecture, the famous conjecture of Birch, Newton, and Dye in the 1960s. So what these guys did, again, in the basement of Cambridge University, they were literally plotting using the very, very early versions of the computer, and probably involved like punching cards on paper and plastic. And they were able to plot ranks and conductors of elliptic curves and make a fundamental conjecture about the relation between the rank and certain analytic properties of L functions. So I won't talk too much about the BSD conjecture or about the memorization conjectures of elliptic curves, because I think Qiu Huan is going to give a talk later. So I'm grateful to him, and so we'll leave that to his talk later. So in terms of, so here's an experiment, and I wish I were there in person, so I can see the eyes of the audience. So I'm just going to start imagining what the eyes of the audience are doing. So if I give you a sequence like this, and you can probably tell me immediately that this is whether this is what the next number is. And a sequence like this is a little more complicated, but after a few minutes, I think you'll probably guess that this is a sequence which decides whether something is a prime. It's the prime Q function for odd integers. Obviously, for evens, it's all zero. So this is one if it's true. This sequence is a little more difficult. And just to cut to the chase, this one is the shifted version of the Liouville lambda function. So this is I'm just recording the integers from 1, 2, 3, 4, 5, 6, and then it is the parity up to multiplicity of the prime factors. This is an extremely hard sequence to predict, and if you have basically to get a handle on predicting this one, there are equivalent formulations of the behavior of that to the Riemann hypothesis. So if you can get this one really, really well, then you have a really good shot at understanding Riemann. So just to quote Hardy, what are we at the end of the day? In terms of mathematicians and theoretical physicists, we are makers and recognizers of patterns, right? So and if there's anything that AI can do better than humans, it's pattern detection. And this is why I'm trying to argue that top-down mathematics is a very, very promising field for AI-assisted fundamental research. So bearing this in mind, so let's just throw this thing to, say, a typical AI system. So predict the next number, right? So you can even try this on ChatGPT. So if you type something like this into ChatGPT and ask what's the next number in its sequence, ChatGPT will tell you that it is 0 because it's recognized its periodicity. This is quite impressive. However, ChatGPT can't do either this one or this one. It will just, it hasn't been trained on enough data of such a type to be able to do something. But nevertheless, we can do something more sophisticated. You can make this into a binary classification of a binary vector problem, right? So this is obviously I've made this a little more standard by making all this into binary vectors. So one thing you can do is to just create a sliding window, say of length 100, and try to predict the next number. So what do I mean by that is you just take a window of a length 100 or so, and then just mark the next number, right? And then you slide it along, and then you predict the next number, slide along. So what this does, what this gives you is a binary labeled set of binary vectors, which is a very standard thing that people like to play with in machine learning. And then you can pass such a problem to your standard classifiers, like support vector machines or Bayes, and you'll very quickly find that for the very before I get to this, so you have this labeled database of binary vectors, and then you can do your standard cross validation, and you train on a certain percent of it, say 80%, and validate on the remaining 20% or 50-50, however you want to do it. And you can record the precision, which is the naive percentage of agreement. And then you can also do some standard things like F1 score or Matthews correlation, which is essentially Matthews correlation. I like because it's -1, 0, or 1. 1 is complete agreement, 0 is random correlation, and -1 is complete anti-correlation. So it has that extra sign. So if you try this to your standard classifiers, your Mod 3 problem gets 100% precision and 100% chi-square, which is great. I mean, this is it shows that this is a trivial linear transformation problem with pretty much any of these classifiers. The prime Q problem, if you play around with it, you get 80%. I don't know why it's doing a bit better than 50%. I think it's probably picking out some kind of sieve method. And I anticipate your questioning. Well, maybe it's because the primes get rarer and rarer. So I I actually tried to make the window size adjusted according to log x over x, but even after that, you still get about 80% true. And it would be nice to know what exactly is doing under the hood. The Liouville lambda function, what it's doing is, of course, I couldn't break the 50-50%, the 50-50, right? So it's just basically 0.5 means that it's just doing complete random guess, and then it's zero, essentially zero chi-square. And I think I've learned this word from Mike. He calls data of such a type Platonic data, right? So this is, I love it. This is a great word. And I think what top-down mathematics boils down to is machine learning techniques applied to Platonic data, right? Which I think Mike talked about in his opening lecture last week. And this reminds me of this wonderful quote of the great Arnold. And Arnold said, famously said, mathematics is a branch of physics where the experiments are cheap. So this is kind of it's a great quote. Applying machine learning to experimental data has been around since at least the late 80s, early 90s. For example, at CERN, people, you can't possibly discover the Higgs, for example, without incredible amount of machine learning, because there's so many petabytes of data running about. But that data is fundamentally different from the kind of data that we're talking about here, because experimental data is prone to error. There's a lot of statistical fluctuation. Here we have exact data that has no margin of error, and it is what it is. You can make statistical inference from it, and which has inherent error, but the data itself, I mean, unless you've made a mistake, it has absolutely no variance or statistical error. So this is, I like to quote my friends Jim and Fabi and Sergey. This is a sort of rigor with machine learning, if you wish. And I like this word Platonic data very much. So just a little bit, how did I get into this whole business? I mean, I really started doing this kind of experimentation really from algebraic geometry, right? So just to give, since this is a broad audience, let me just give you a little bit of motivation about where this problem even comes from, and why we had why we have at our fingertips such a large amount of data in this sense. So let me just forget about everything I've said so far. Let me just have a slight digression for about, say, 5 minutes. So the initial problem from a mathematical point of view is the generalization of this famous diagram, right? So this is a classic problem. I put it as 1736. I think that was the year that Euler invented topology. It's a famous result that compact boundaryless surfaces and compact orientable boundaryless surfaces are classified by single integer, the Euler number, right? But what is really interesting is that there's a trichotomy in this classification. So there's basically positive curvature, zero curvature, and negative curvature. So basically anything, genus 0 is the sphere is the positive curvature. The torus, the two torus, or Clavier dimension, complex dimension 1 Clavier manifold is zero curvature, and all of the higher genus are hyperbolic objects that have a negative curvature. And the point is that these things can be complexified into Riemann surfaces. So these are real dimension 2, but complex dimension 1 objects. So this is where you require the orientability, because to make them to endow a complex structure on these things, you need these things to be oriented. So that's why I don't have Mobius strips and things like that here. So it's a very beautiful fact that I think Gauss considered this his greatest work. He calls him his theorema egregium, his great theorem, is to be able to relate curvature to these things to the genus, right? So and it really traverses many different branches of mathematics just to be able to write this diagram for Riemann surfaces. Right? So what's interesting is, of course, if you want to generalize this to higher dimension of a positive curvature, zero curvature, a negative curvature, so they in algebraic geometry, in complex algebraic geometry, these are generically known as Fano varieties of general type, and Ricci-flat varieties or Calabi-Yau varieties, Ricci-flat Kähler varieties. So they're in this bounding case of zero curvature. And generalizing this diagram to higher dimension is the heart of the minimal model program. So okay, so this is cool, and this is certainly at the heart of topology, geometry, differential and algebraic geometry for 200 years. And what is really interesting is that and it's conjectured by Calabi in the 1950s that a similar relation where the Chern class controls this curvature was the famous conjecture of Calabi, which you can read here. I won't bother with the details about this is that's why the Calabi conjecture was so important. Is that at least for Kähler manifolds, this beautiful relationship between Chern class and Ricci curvature is the generalization of this diagram. And of course, famously, this conjecture was proven by Yau in his Fields Medal-winning work in the late 70s. So let's just park that for a minute. And so this is a development in topology and geometry for about 200 years. So in comes string theory. And so superstring theory is this theory in 10 dimensions. And we need to reduce this 10 dimensions somehow to our visible world of 4 dimensions. So you need somehow explain away, either by compactifying or by what's known as sort of the decompactifying of these 6 extra dimensions. And then this beautiful paper in the mid 80s showed that one of the solutions, the standard solution, I must emphasize, is not the only solution, but it's one of the standard solutions for these 6 extra dimensions, is precisely to be this Ricci-flat Kähler manifold of dimension 3. So this is where Calabi-Yau, so the story is, it just so happens that in the late 80s, Strominger and Yau were at the IS in the same corridor. So and then these guys were able to ask Yau about these strange things that physicists were thinking about, which are Ricci-flat Kähler manifolds. And Yau said, well, that's great, because he just got the Fields Medal for precisely this work. So this is a beautiful time when physics and mathematics were meeting together. And the point is, so this idea, in fact, the word Calabi-Yau was I think coined by these guys in honor of Yau's proof of the Calabi conjecture. So this is why this 200-year problem in topology and geometry finds its natural emergence in theoretical physics for the first time. So here's an interesting fact. As I mentioned, in complex dimension 1, there is only one topological type of a Calabi-Yau manifold, and that's just the torus or elliptic curve. If you realize that algebraically, in complex dimension 2, it just happens there is the 4th torus and the K3 surface, which there's 2 of them. And in complex dimension 3, this is the Calabi-Yau 3, the one that we're interested in, because you want to get rid of 6 extra real dimensions. You would imagine that it's not that much, right? The sequence goes as 1 in complex dimension 1, 2 in complex dimension 2, maybe 3 in complex dimension 3. But unfortunately, this is a sequence that doesn't go like that. In fact, it goes as 1, 2, and we have no idea, but we know at least about 1 billion of these things. And it just a fact of life that this happens to be a problem in algebraic geometry where it exponentiates in the number of possible topological types. It is still a conjecture of Yau that within every dimension, this bounding case of Ricci flatness is a finite, is finite in topological type. It's a theorem that final varieties in every dimension, there's only a finite number of topological types. But and we know that the general varieties of general type there's an infinite type, and it's probably even uncountably infinite. But it's the hope and a conjecture of Yau's that this boundary case of Ricci flatness is also finite in topological type, but it's still an unsettled problem. But anyhow, so in 3 dimensions so far, since this 1985, there's been tremendous work by string theorists and algebraic geometers and computer scientists later joined in to just classify, various different topological types. And this number just keeps on growing. And as far as Calabi-Yau manifolds, the biggest impressive list is by Kurtz and Schkarke, where they realized this Calabi-Yau manifolds as hypersurface in toric varieties. And even that it's already about 500 million just coming from the polytopes. So this is a very impressive list. So the idea that there is this proliferation became known as the string landscape problem, right? So there's just so many possible, even just Calabi-Yaus, let alone other possible solutions to the string theory compactification issue. It became known as the string landscape problem. Is there a selection criterion? Can we put a metric on the space of this? Why is our universe the way that it is? Became one of the central problems in string theory that at least probably the biggest theoretical challenge in string theory in the last 30 years. So Mike was one of the pioneers in thinking of, what is the statistics of the entire space of string vacua, right? And then the number just keeps on growing. There's this paper in 2003 of KKLNT, which puts type 2 string theory to 10 to the 500. So this number basically comes from the typical Calabi-Yau and the typical algebraic cycles on the Calabi-Yau. And this number keeps going. And then F3 estimates have come to this. So there's a recent estimate I think by Jim Halverson and friends on F3 estimates, which is also in that range. So that's why we have the good thing. So that's the bad thing. We have so much of this, but the good thing is that we actually have a lot of this recorded freely on the computer. So by the turn of by the 2000s and 2010s, physicists and mathematicians already have access to very, very large databases for Calabi-Yau manifolds. And so that's why I was doing one of these, I was just playing around with this kind of calculation. So a typical calculation is to realize this Calabi-Yau manifolds as complete in its sections. So for example, here, you can see a manifold as multi-graded polynomials. Hypersurface intersections of hypersurface. So each column is a multi-degree polynomial embedded in some multi-degree projective space. And then at the end of the day, you want to compute some topological invariance like this, which counts, say, the number of fermions, right? So the standard way to do this, of course, is to do sequence chasing until you're blue in the face, right? This kind of computation, which Macaulay 2 and things can do, but because the complexity of doing this polynomial system manipulation is double exponential algorithm in Grosvenor basis, so it's extremely difficult to do in general, right? So the I'm giving, there we go. So back in 2017, I was thinking, well, how different is this kind of problem being labeled by this kind of integers different from your typical problem in machine learning, which is to tensorize or pixelate your problem and then try to see that as a kind of image recognition problem. So I've since become a complete fanatic. So I'm just going to say, like algebraic geometry is an image processing problem. And so far, I have not been shot by algebraic geometry. So there must be some level of truth in what I'm trying to say here. So 2017 is a good year because many of my friends were independently thinking about using machine learning technology to try to map out the string landscape. So there's so you can see they're all in 2017 in different aspects of trying to escape, trying to use this problem, using this new methodology of machine learning to attack this string landscape problem, the string vacuum landscape problem. And 2017 is also good. And if you remember, that was also the year that AlphaZero was developed, and it was also apparently the first paper on the transformer. And it was also a year that Sophia, this robot, which looks very primitive now by today's standards, actually gains a human passport. And also, of course, with our friends here, it was the beginning of the String Data Annual Conference series. So this is very good. Good year it was sort of things were in the air. And of course, for me, 2017 was also a very good year because my son was born. So this is a very personal thing as well. So basically, since then, there's a growing community which goes under the rubric of string data, and then later emerged in another. So string theory is really the string data series is really for theoretical physics minded people. And there's another parallel series which started, I think, 2019 with Tom Oliver, Al Kasperczyk, and later with Qiuhuang Li, which is called Danger. That's another series of trying to explore this Platonic data with machine learning techniques. And I think Danger stands for data in analysis, number theory, geometry, and representation theory. Somehow, I think this is Tom Oliver's great insight that these fields of mathematics spell danger. So since 2017, I've been I'm grateful to my fantastic students in exploring this landscape of problems, not just in the string landscape, but increasingly so for me, just the landscape of mathematics. So basically, the one thing that I enjoy doing more than doing mathematics is to do mathematics with friends. So I made friends in almost every field that I could get my hands on, and I just try to learn something new from them and try to take their best Platonic data and try to explore them. So you can scan this QR code to find the I should include the photos of the people. There's just too many. I've made a lot of friends since then, which is a very, very good thing. And I've certainly learned a lot from them. And I want to mention that the fact, for something I'm going to mention later, the fact that I had to get human advice is something that limits us, right? So we're not quite at the stage where you can feed Platonic data into some AI system or chatbot or whatever you want to take, and then it'll start generating conjectures on its own, right? We're not quite there yet. And this is why human expertise is really important. But nevertheless, I think we might be inching towards that direction. But at least for the foreseeable future, I think the future of mathematics is certainly a collaboration between the human expert and the proof co-pilots, as well as AI-guided intuition. So 2 books have come out since then. So please buy these books. One is a textbook and one is an editorial of various directions on this. And so buy these books so I don't have to, so I can get like my £10 a year royalties. So here's something that I want to sort of finish up with in the remaining time, which is a more stringent test for AI-guided AI-guided mathematics. All right, so this is, I'm sorry, this is a bit too small. Let me see if I can even expand it. So this is a conference which I organized with these people and in Cambridge last year. And so you can read from the title. The title is actually longer than this. It's supposed to be Black Holes, Bridges Between Number Theory and the Holographic Quantum Information and Machine Learning. But because it's so long, they won't let us have so many characters. So basically, it's everything under the sun. And the point of this conference that we were running was just to try to bring as many friends as we could to participate in this dialogue between physicists, mathematicians, and AI experts, right? I mean, so, as I mentioned earlier, one of the greatest things about string theory in the last 20, 30 years is that it brought mathematicians and theoretical physicists together. And I think in the last 10 years or so, 10, 15 years or so, there's this real dialogue between mathematicians, physicists, and computer scientists, and now AI experts to push in the next major collaboration and direction in fundamental discovery. So while I was at this conference, we were kind of, people like Buzzard and were there, and we were watching this talk by Birch, and we were quite inspired by this talk. And bearing in mind that ChatGPT passed the Turing test in 2022, we were thinking, well, would it be nice to have something that that's more stringent than the Turing test, right? So this is what I mean by that is, we've got this machine learning of mathematical data, of this Platonic data, in Mike's words, and you're just trying to say, and you're trying to do two things. One, to make conjectures, precise conjectures in mathematics, and or to get precise pathways towards proofs in mathematics or derivations in theoretical physics. Obviously, if you try ChatGPT, it's not gonna help very much yet. ChatGPT is about the level of a good undergraduate, right? So I think ChatGPT can solve first and second year undergraduate problems fairly well, but it certainly can't help us in real day-to-day research. But nevertheless, it's passed its Turing test. And now, if you use more sophisticated AI algorithms to try to make conjectures or to make pathways in your proofs, surely we need something more stringent to see what a test should be. So we have jokingly formulated the Birch test, and this is of course named after in honor of Birch. And so we reported this in a very short correspondence. So what is the Birch test? It's somehow like a much more stringent test on AI-guided conjecture formulation and AI-guided human intuition in mathematics. So, and to summarize what this test is, it comes down to the acronyms AIN. So that's why it's called the AIN on AI. The first test that it must pass is automaticity, right? The conjecture must be generated by AI in the following sense that if I feed you a Platonic data, if I'm guiding constantly, with human expertise or telling what the AI system should be doing, that's not so good, right? Because you're sort of building human bias into it. So this A is very, very difficult. And I think Hui is going to mention a bit later on the importance of the human-guided aspects of this in the memorization conjectures. And the second one of obviously I is interpretability. And of course, there are many machine learning experts in the audience. And I think interpretability is clearly one of the biggest challenges to AI research, especially for deep neural networks. Just because some deep learning algorithm can do something extremely well, even if it's pure mathematics, if you can't untangle out what all the layers are doing and actually get a concrete statement out of it, it's not so good for a research mathematician. So that's the I. And three, it has to be non-trivial enough in the sense that, we're already at the stage where if you start feeding Platonic data into some AI system, it'll start generating, hundreds and thousands or millions of conjectures every single day. But how do you actually pick out the ones that are interesting, right? So how do you select from this? I think Challenger Mishra and friends have been working on this thing called conjecture space, which I think is a very interesting way to try to look at this problem of auto selection of what interesting conjectures are. So that's the AIN on AI. And of course, most importantly, you have to make Birch happy. And that's I guess in that sense we have to make that's why it's named the Birch test. Interestingly, Tom Hodgkinson, who is our science writer here at the London Institute, he's an Englishman, and he says apparently birching is a verb in English. And it's a terrible word. So back in the day in school, Victorian times for sure, if you misbehave, I think in America we call it caning. But in the if you get caned on the hand or something, or on your back. But in the old traditional schools in England, they're called you get birched. If you misbehave, you get beaten by a birch tree. So Tom Hodgkinson very astutely points out that this birch test is essentially what you're doing is to take a birch tree and tree branch, and you're beating an AI system to try to generate correct conjectures that will actually lead to interesting mathematics. So what have been some of the candidates of the Birch test in the last years? So and I will say that so far, but before I even get there, strictly nothing has passed the Birch test, right? In some sense, right? Because we don't have a completely fully automated system that conjectures something that's all of the above. All right. So now we'll try to explain why this is the case, or how is the case, not why, but how. So for example, my early experiments in topological invariance, I mean, that fails the eye test right away, right? Just because some deep neural network is able to compute this problem. And I think at the time I was doing very primitive things, but now this calculation has been improved by people like Finatello and collaborators to like 99.96% accuracy using the inception network, Google's inception network. But it's fantastic that you can actually look at this and compute this topological invariant, this Hodge number, but we have no idea what the actual neural network is doing. So this fails the eye test. Here's one that's really interesting, and and there's something I don't quite understand. And this is a problem that's suggested to me by Minyoung Kim. If you take the Cayley tables of finite groups, right, and you just you take the first 100 or so, can't go too high because it gets very expensive afterwards, and you just permuted it, and then over permute those which are simple groups, and then you have this balanced data set of matrices which are which are marked 1 to n, and then you mark some of them as 1, which are simple, and 0 as non-simple, and then you try to plot in this high dimensional space, and you can actually, a support vector machine will find a separating hyperplane between these spaces. And we tried just earlier this year, we tried this again with Jijala and Mishra on other representations of finite groups, like generating representation. And this phenomenon seems to persist. So there's a fundamental reason why certain groups are simple just by looking at it. That's very interesting and could lead to potential new ways of doing representation theory. But again, this doesn't pass the eye test because this wasn't precise enough, right? What is this hyperplane? And you can tell me the equation, but how does it help with actual proving a proof strategy of why this is happening? There's another one. So this is a landmark paper, and it's a beautiful collaboration of DeepMind, Alex Davies, and Jody Williamson, and friends in Oxford like Andras and Lazenby. They were able to get, this is a really beautiful one, which is they were able to get salient. They did a saliency test on what the Jones polynomial could possibly depend on, right? And they were able to extrapolate out a new relation. Well, they did a saliency test on what it could depend on, and then they were able to get on the features that it could depend on, and then they did a regression model on that, and they were able to get a completely new formula for the Jones polynomial, which is very nice. So this one passes the eye test. It was interpretable because you actually get this formula. It also passes the A test. at least partially passes the A test, because it was the AI that was doing the saliency test. They weren't so much being guided by humans, so it passes the A and the I. And I think in some sense, this paper really passes A for the first time, but it didn't pass N. It wasn't non-trivial enough, right? In the sense that the formula they got, to my understanding, I'm not an authorist. Maybe Jim can remark more on this later in his talk. That it wasn't a groundbreaking result in knot invariance. So well, I don't know. Maybe I'm making you pessimistic in saying how these things fail the various Birch tests, but the hope is we're inching towards, we as a community are inching towards something that passes A, I, and N. And then this will be really, really, really interesting in making new strides in this AI-guided exploration of Platonic data. And there are other ones. There's this beautiful paper in Nature.com of Coates, Kaspersky, and Veneziale, where they were able to predict final dimensions from quantum period. Again, this fails the I test because it doesn't. The deep neural network is not interpretable. So of course, I'm just giving some examples. There've been, I think since 2017, there've been over 200 papers on AI exploration of various aspects of Platonic data, and I think various talks, even in this closing program, will report various aspects of it. And again, for example, this one, we were able to apply for a genetic algorithm we found a new Clavier fourfold. Okay, that's nice. Again, it's A. I mean, we didn't do anything. The genetic algorithm was finding something. And it's clearly interpretable because it was able to find a Clavier fourfold, but it's certainly not non-trivial at all because you just found some new Clavier fourfold. Something that has passed the N test, which is the non-triviality, and I'm happy that I don't have a report on this, is the murmuration phenomenon, and this is done in collaboration with Qiuhuan Li, Tom Oliver, and Alexei Pozniakov. And then with a paper to appear joint with Drew Sutherland. And then this murmuration thing made Kevin and almost happy. And well, by inference, Bertrand was happy. But they weren't entirely happy in the sense that human intervention was needed. But this is important, and I'm just going to spend the last 2 minutes or so just mention a little bit about the discovery of the murmuration phenomenon before passing this to Qiuhuan, who's going to give a detailed talk about this. So as I mentioned earlier, there have been various experiments in machine learning experiments in number theory. So for example, I mentioned this prime Q. Also, by the way, I think if you try to just feed this into a sequence predictor, it'd be very, very, very hard to be able to just do it. And what's really interesting is that this Liouville lambda thing was actually, I think Peter Sarnak was one of the first questions he asked Google DeepMind. I think at the time it was still called Google DeepMind, to predict this parity of factorization of prime factorization up to multiplicity, and you couldn't do better than random guess. So in 2019, obviously there is this beautiful data set called the LMFDB, let me try the L functions and modular forms database, of which Drew Sutherland has been the instrumental in creating. And this is a database that has everything you ever want to know about elliptic curves. Just like I mentioned earlier that in the physics literature, the Kreutzer-Shkaka database of Clavier threefolds, which are hypersurface toric varieties, is our go-to big data set for Clavier compact Clavier smooth varieties. So that's about 473 million. And the LMFDB, I mean, you can ask Drew, who's in the audience. It's a beautiful set. I think it's on the order of 10 million elliptic curves on everything you ever want to know about the arithmetic geometry of your elliptic curves, in particular, those quantities associated with the BSD conjecture. So I joined forces with two data scientists. So basically, none of us, no one in this collaboration knew anything. None of us are is a card-carrying number theorist, right? So we explored the LMFDB in the following sense. So this is a very precise experiment that we did, which is to take the Weierstrass representation. You can find it. So this is the standard cubic, right? So it's y squared is equal to x cubed minus g2x minus G3, and then G2 and G3 are the Weierstrass coefficients. And then it's all documented in LMFDB. So you take these things, and what we're trying to do is can you extrapolate from these two non-trivial coefficients the rank of the elliptic curve? And we got complete nonsense. We could not predict anything. So I got very depressed and said, well, I think number theory is just very, very hard for machine learning, right? And that's very important because, well, it's important that, well, I was approaching it from a point of view of an algebraic geometer who is, I'm naturally, I want to use a Weierstrass representation. Yeah.
I wish we had more time, but you better wrap up.
Yeah. This is the last slide, actually, because then this is where I'm going to turn to Qiuhuan. And that's exactly the point where I met card-carrying number theorists, Qiuhuan and Tom Oliver, and they told me not to use the Weierstrass coefficients, but use the AP coefficients. And it is from there one could discover something new about the properties of elliptic curves. So, and this is an advertisement really for Qiuhuan's talk later. So just to wrap up, over the last 3 centuries, this idea of conjecture formulation, in the 19th century, the eyes of Gauss were good enough. But the 20th century, you really need computer aid to make some fundamental and deep conjectures. And then clearly in the 21st century, it's going to be a collaboration between human and AI to find new conjectures and indeed new proof using proof copilots, a new discoveries in mathematics. So I think I'll stop there. Thank you very much.